you very much for that introduction. Good afternoon, everybody. I'll do my best to keep you all awake after that very nice lunch that we had. So, this paper discusses a patented actuation technology for fuel injectors called Injectors, which provides piezo-like performance at solenoid cost. Sentec has licensed this technology for gaseous fuel injectors and is seeking future partners in GDI and diesel fields of use. During this presentation, I will discuss some of the challenges to GDI injection systems currently available and how Injectors may fit in to the product mix, and to illustrate the technology of Injectors and present some performance test results. Just to start off with, just review some of the top level drivers on injection systems. Obviously, it's required to get an injection system which will provide plenty of torque and performance, so it's a fun to drive vehicle. You need to achieve a good fuel economy, and obviously at the moment we heard this morning there's lots of issues with regards to emissions, especially particulates in gasoline fuel injection in the future, and there is interest in reducing the cost, so get a best cost benefit ratio. And one of the key things for getting the particulates down is being able to provide very repeatable fuel injection events, very small injection events of fuel, maybe below 1 milligram per pulse. And the idea is with this multiple fuel injection, that may be possible to avoid the requirement for gasoline particulate filters, which we heard about earlier today as well. So some of the GDI technologies that are available on the marketplace today are technologies that use a piezo stack to drive an opening outward valve. These are very precise, can achieve 1 milligram per pulse, very repeatable, maybe 2 milligrams per pulse. These potentially have the ability to avoid the use of a GPF. However, combined with the cost of the piezo and the thermal compensator and the specialised drivers they require, it may not be an economical solution for the whole of the marketplace. An alternative to that is the solenoid-based GDI technology. However, this may not have the capability to get down to 1 milligram per pulse with high repeatability, and so therefore the use of a GPF may be required, which then increases the net cost of the system. So this is where Injectors has been designed to fit in, is to actually provide the capabilities of the piezos technology, but at the cost comparative to the solenoid technology. So Sentec decided to manufacture some prototype injectors, and we based that on an opening outward injector, and we use a fuel valve which is opening outward with an actuator here above it that drives the actual fuel valve. And this is a development injector here with clamps on the outside, and this injector here is sort of a conceptual design of what it would look like if it didn't have the clamps. So it's be the sort of 20.7 millimeter external diameter that is required in the industry, and this has been tested by OEMs and has achieved capabilities of 1 milligram per pulse with a 2% 3 sigma over the mean repeatability, so which may enable the avoidance of a GPF. So I'd like to share some results with you a bit later on, but to start off with, I'll just go through the principle of the technology. So if we concentrate on the left-hand side here first, this is a representation of an opening inward injector with a ball seated here, with the armature and the top pole piece here with a coil. And what happens is once the coil is actually energized, the armature is sucked up to the top here and opens the ball seat arrangement and allows fuel to flow through the injector. The Injectors technology, which you can see on the right-hand side here, has many of the similar components. However, there's a lower pole piece as well as an upper pole piece. There's 2 working gaps, one above and below the armature. This means that there's a constant working gap in this technology, which makes the technology more linear in its reluctance, its magnetic qualities, compared with the standard injector. And the technology also employs a radial magnetized ring magnet, or arc of magnets in yellow here, which actually produce a flux all the time, even when there's no current passing through the coil here. And the technology also uses a stiff spring as well, stiffer spring than the spring that would be found in a normal coil. So the main difference in performance that you get between these is that this tends to be more of a bang-bang type device. It's either open or it's closed. With this technology here, you can actually achieve stable partial lifts between the lower and upper lift positions, wherever you like, and it has a good feedback due to its very good electromagnetic coupling, which helps with its control. So the 3 illustrations here just show how the flux is actually switched from the permanent magnet depending on the position of the armature. So if the armature is in the center, that acts as a conduit to take the flux to the upper pole piece and to the lower pole piece and creates no force on the actual armature, whereas if it's on the top position here, the force pulls the armature upwards from the permanent magnet, and if it's in the bottom position here, it comes down. And what turns out to happen is this turns out to be a linear, near perfect linear magnetic spring. And then how do you get the actual solenoid to switch? How do you get the actuator to switch? Well, what happens is this is a situation where there's no current flowing on the left-hand side here. So there's a net downward force in this instance because the armature is at the bottom and the flux has been bussed down here by the armature. And then when you apply current to the coil here, that generates a flux that's in the counter direction to the actual flux from the permanent magnet, and that generates a net flux in this upper part which lifts the armature upwards, and as you carry on moving you increase the current and you can generate a very high vertical force upwards on the armature to open the injector, for instance. So in this slide I'm showing that you have the stiff spring here. That is of a stiffness that actually is higher stiffness than the magnetic stiffness of the actuator I was talking about earlier. And it turns out if that mechanical stiffness is higher than the magnetic stiffness, you can get stable partial lift positions. This spring also is of offset, so the force it generates onto the armature is significantly high enough so that it always generates a sealing force here at the seat. So if there's no current flowing, the injector will close and you seal. On the right hand side here is showing a graph of its, the force generated in the vertical axis against the current going through the coil against the displacement of the armature. So the blue line is where the actual ball is seated, the red line is where the ball is fully lifted to the maximum lift, and the green line is an intermediate position. And basically what this is showing is when you've actually got zero current flowing, there's a net force downwards of tens of newtons that actually creates a seal down here at the tip, and as the current is moved up along this axis here, you generate a net force which actually allows you to actually create a stable partial lift wherever you like between the lower and the upper stroke positions. So for instance, if you have this current here, that generates 50% lift. If you put the current in here or above, it generates this higher lift. So what this really is showing is you've got a linear actuator, so you've got a linear increase in displacement with the actual current being applied. If you applied negative currents, you can also generate a negative force on the armature, which is something that obviously you can't do with a standard solenoid. And that could be useful if you wanted to close the injector faster, or you want to hold it against some pressure, or whatever things you needed, if that was something you wanted to have. It's also got a lot of feedback from this armature position in the signals that are used to displace the armature, and this is used for closed loop control. And this technology can be used for achieving lifts of, say, 5 microns up to 30 microns, say, in one injector, or injectors may have up to 1,000 microns in displacement, and it could be used for that application as well. So it's got a wide range of strokes that can be achieved with the technology. So I just want to present a few results from the opening outward GDI injector that we tested, and this is some results we did in-house. And what we've got here is a needle lift in microns, and this injector had a maximum lift of about 30 microns, and you can see this is showing microseconds here. So basically we were able to achieve a lift, say 40% full lift, and hold it there for 1 millisecond nearly, and the same at 20% lift. And we were able to also then energize various pulse widths as we're increasing pulse widths, and these are the deliveries here, and you can see we can achieve various gradients of linearity of milligrams per pulse against pulse width. So it makes a flexible injection system, gives you an extra a dimension of adjustment in a gasoline direct injector. This is some results showing the actual speed of operation. There's around 150 microseconds between the logic and the start of opening, so it's very fast, and it achieves 30 microns of movement within about 200 microseconds, and holds a nice stable position here, as you can see, for an extended period of time, and then it closes very quickly. And over here again is a linearity curve of the delivery against the pulse width. And you can see in many injectors there's like a ballistic region, and then there's a reduction in fuel being delivered as pulse width increases before it then goes into the linear region. You see this injector doesn't have that, which is a good thing. These are some test results which were completed by a leading OEM in their laboratory using an Acrobis shot-to-shot metering system, and we used our own Sentec driver for this, for driving the injector. And what we've got here is milligrams per pulse against milliseconds. And the blue line is the sort of linearity curve of fuel delivery. So we're going down here to sort of fractions of a milligram up to about 20, 30, 35 milligrams per pulse. So you've got a nice straight delivery with no inflections in there. And this is the actual repeatability here in the red. And this is, so basically all these are below 2% repeatability, which is a very good level of repeatability. And on the right-hand side, we can see an enlargement of this area here, so it's a lot more detail. You can see that we're getting 1% repeatability at less than 1 milligram deliveries, which is far in excess of normal solenoid technologies that are available on the market. So this is another set of tests that are also done at leading OEM, again with the Aquator metering system. For each of these positions, again, there were 100 shots at each of these deliveries. Difference between this one and the earlier set of graph was that we used just a standard peak and hold GDI ECU that was available in the lab at the time. So it's just a standard one using standard type of voltages and currents for energization and holding, and we're still achieving at 200 bars less than 3% repeatability at around 0.6 milligrams per pulse. Just to show a bit of the capabilities of the technology, we also did some testing at IAV, Gifhorn, in their facility using a IAV rate meter. And so this is a rate of injection here in the vertical axis against the energization time. And we sort of had some rate shaping, so we stepped up from 0 to 2 milligrams per millisecond, 11 milligrams, 8 milligrams, and back down. We can change the ramp rates between the different rates as well if we want to. And then over here we did some multiple injections, and you can see we get down to something like hydraulic dwell of about 70 microseconds in this testing. So each of these delivers around 4 or 5 milligrams per pulse. We also did some internal testing in Sentec in our lab. We built ourselves a spray momentum test capability, and we were able to achieve 5 1 milligram per pulse injections within 1,000 microseconds, which may be useful for stratified charge applications or something like that. We also did some work to look about the interaction of fuel injection events, and in this instance we had an 8 milligram delivery, and then we had subsequent 3 milligram deliveries and brought the 3 milligram deliveries closer to the 8 milligram delivery to see how they interacted. And this curve over here, or straight line as it turns out to be, actually showing the net delivery at various electrical delays between the two injection events. And you can see you get very consistent results. Which may be important for things like cold start and other applications where you're trying to control the emissions. And here's another series of tests that we did where we're measuring displacement of the needle of the injector, and we had 2 pulses of sort of equal size, but bring them closer together, and 100% represents no difference between the 2 pulses. And what you can see as we bring the 2 pulses closer and closer together, you start to get some interaction, and this is when you're getting down to 0 electrical delay between the 2 injection events. you get something like 5% difference between the two injection events. But as soon as you get over about 100 microseconds of electrical dwell between the two, you get down to less than 1.5% difference between the two injection deliveries. This is just giving a little bit of information about the closed loop control capability of the technology. In this experiment, we had our closed loop system running, and what that's actually doing is measuring the currents and voltages being applied to the injector, to the coil. So there's no extra feedback other than that. And what we did was we ran the injector constantly, and we're measuring displacement, so it's 10 microns of displacement for each injection. And what we then did was the injector was rated to 200 bars. We reduced the pressure down from 150 bars to 100 bars, and we note what happened was that generates quite a large differential force on the actual fuel valve, and so that led to minus 20 microns of lift instead of the 10 microns. And within the next pulse, the control system was able to monitor that from the feedback it got from the solenoid coils signal, and get back to the 10 microns displacement that was the target. So this could be useful in the application where there's variations in the manufacture of the injector or in the operating conditions of the injector. This feedback could be used to actually compensate for that, just as it is in piezo type injection systems today. And then this is my last slide. It basically summarizes what we've been discussing, I've been presenting so far, and we have looked at the technologies that are in the marketplace today. We've reviewed the principle of the technology behind Exactus with its two pole pieces instead of one, which can give you up to twice the force per unit cross-sectional area compared with a standard solenoid injector. And we've also been through some of the performance capabilities of our prototype injectors that we've built, which have been tested in-house at Sentec and also externally at OEM and by IAV. So Sentec is carrying this technology forward and is looking for partners in GDI and diesel fields of use. And thank you very much for your attention.